Okay, so we were here computing edges. Vamos a ahora, anda. ¿Cómo lo va a tener? Pues voy a llegar tarde sin traer un chiste. ¿De qué? Pues voy a llegar tarde sin traer un chiste. Well, okay, so we were here, we were computing edges, and let us go to one dimension first. See what is an edge. So let's say that you have a signal. You have a signal. This is t. This is x of t, and then your signal. Signal is like this, and then in here you have an edge. Okay, so you have an edge here, and you have another edge there. How can I compute an edge? How can I know that I have an edge there and not anywhere else? Because I can compute the derivative. If I compute the derivative, if I plot here, say x prime. So if I compute x prime, I have an edge there, and then I have another. So I have a Dirac delta there, and I have another Dirac delta. And this goes up because my edge is from left to right, and here my edge is from right to left. So left to right, and this is, yeah, so this is a positive edge, this is a negative. Okay, so what is x prime? So let's think of x prime. So x prime is the limit when delta t goes to 0 of the function divided by delta. Okay, so this is the limit when this interval, this delta t goes to 0. But now let's say that we have a sample signal. So we have this signal, but we have this one. So we have samples here. We have samples, and our sampling is delta t. This is our sampling. Okay, so then I can express this, can approximate like this. So I can say this is, let's make it red. So this is approximately. Now I don't have any limit anymore because I have a fixed sampling. So this is the sample at n plus 1. This is the sample at n. And then divided by the sampling set. If I forget about this one, so I can say that this derivative is proportional. This is proportional to x n plus 1 minus x. Okay, so it is simply just dropping down a scale. So scalars, that kind of dummy things. So it depends on what is your purpose, but most of the times we don't care about scalars. And we could have defined it in this way, but we could also define it in the following way. So we could also have said that this is the limit of x of t minus x of t minus delta t when delta t goes to 0. You may remember this is the derivative when you come from the right. This is the derivative when you come from the left. You may remember these two definitions of derivative. And then at the end, if you take samples, you have said this is x of n minus x of n minus 1. Okay, so we can compute derivatives or approximate derivatives taking one sample on the right and the current sample, or the current sample and one sample on the left. Okay, so let us look. Yeah, so let's say that I want to construct a signal. I want to construct a signal that approximates this derivative. So let's say that I want to construct. Still use y red. So let's say that I want to construct x that is equal to this. So y is equal to that. So this is an approximation of the derivative. I can express this thing as x of n on all with what? Delta n minus 1 minus delta n. I could also have said the same, something similar to this. So this is a y1, this is an approximation of the derivative, this is another approximation of the derivative, and this is x of n of delta n minus delta n plus 1. Actually, this should be like this. Okay. So far, so good. Yeah. Okay, so that means that we can compute derivatives by convolving with a couple of deltas. And these deltas, these are, yesterday we were using this one. Yesterday I was using this one, where we have these two deltas. Remember? And we were convolving with this one. Okay, so let us now go to images. With images, we have the same, but now we have so let's say that I have an image, so I have rows, I have columns, and then I want to compute the derivative. This is a step function, and then I want to compute the derivative with respect to this direction. So this direction, what I have is to use the same kind of expressions that we had before in one dimension, but now only one of the dimensions. And I can use one sample and the one on the left, or one sample and the one on the right. I can use both. So yeah, at the end it is it's very simple, and I would get this kind of derivatives here. So this is a positive derivative. So I'm going from 0 to 1. So when I go from 0 to 1, on this edge I have a positive value, and on this edge I have a negative value. And this derivative is the opposite. So actually, if you look at the signs, the signs are the opposite ones and the ones I have used in the y. And that is why these edges are inverted. So now this one is positive, this one is negative. So this is minus the derivative. But we don't care. We want to detect edges. We don't care. It depends on what is your application, but we don't care in general if it is a positive edge or a negative edge. And then we can add both. So we can add these two, and then we would have this kind of responses, and it is simply just one these two expressions. So we would have this one. Okay. So yeah, now we can detect edges of images, at least in this direction. And for instance, let's say that I want to express that as a convolution. So if I want to express that as a convolution, now we have images. So let's go to images. So let's say my image that is the derivative, let's call it K, at a particular xy will be y, xy. Now convolve with something, with what? Will be, actually if I want to be correct about notations, let's say, because I want to use convolution, discrete convolution, so I should use square brackets. Okay? So the difference between square brackets and normal parentheses is that this signal is discrete here, with the parentheses it is continuous. So now, this will be xy minus twice minus this 1, y minus 1 minus delta y plus 1. And then we would have this same expression as we would have there. Okay, so then next, now we plot those deltas. So now we plot them. So this curve, let's plot it. So let's say this is x, this is y. Okay, so now I have 2 here. That's so I have 2. I have -1 at y minus 1. So this is the origin. So this is the 0, 0. This is the 0, 0 point. Now I would have -1 minus -1 here. Okay, so this is what we are representing there, and all the others are seen. You don't have to represent it. So I'm convolving with this filter. Okay, so so we have the same kind of representation. So these are vertical derivatives, these are horizontal derivatives. I can add both, and then if this is my input image, this would be the output. Okay, so I can detect edges in all directions. Now let's add an example. We have these two images, and I convolve with this one. Okay. I convolve with this one. That means that I'm computing derivatives along this direction. And there are a few things we know. Okay, so the first one is, what about this band? In this band, there are no steps. Only this, here there is a step, and here there is another step. So let's see what happens with the derivative. It is 0 all the time, except that those two lines. What about this one? This one is the opposite. It is just, we have a step. So this is -1, 1, -1, 1 all the time. So we have a derivative that is changing all the time. That is what's happening. And the same happens with all the others. Okay, so if you analyze all these things, so in this direction we get the steps, right? We get these lines, and so on. And then for the house, we see these changes. So changes along this direction. So in all this area, there is no change because this area is very flat. The same everywhere. And we can do the same now with horizontal derivatives, and then it is this region that disappears. And now we don't see, for instance, the border of the roof. We don't see it because the border of the roof is a change in this direction. It's not a change in this direction. So in this direction, there is no change. So that is why it disappears. Then we can add both. Okay, so we add vertical and horizontal derivatives, and then now we see all the borders. And we can also compute derivatives in diagonal. And then, for instance, it is interesting that this square disappears. Let's see why. it is, they are diagonals in this direction. I'm computing the derivative in this direction. So in this direction, there is no change. So that is why it disappears. But this one doesn't disappear. So when I derivative in this direction, this one doesn't disappear, this one disappears. And again, we can compute, for instance, this one, this side of the roof doesn't disappear in this direction, but this side of the roof disappears because in this direction there is no change. I can compute the other direction, I can add both again. You can add all of them. So now we are adding all kinds of derivatives in all directions. And these are the borders that we get. And this is the house again. Any question up here? No? I would like to show you how this can be done. So for instance, you would have, so for instance, this is a review of classic edge detectors. And you go, like, let's say, you take the chairs, and we haven't seen all these names, Roberts, Brady, Sobel, Paralic. These are different kind of estimated derivatives or estimated edges. But let's run it, let's see the result, and then we will see what are the reasoning behind all these kind of. So this is the input. This is the input. Then we can see, for instance, the borders detected by Roberts, the borders detected by Brevin, by Sobel. Sobel is one of the most better known. Paralic. So you may decide which one you like the most. And it is also a matter of parameters. So you have seen that you can change the parameters of each one of these guys. So, yeah, for instance, let's see what is the Previtt operator. Previtt operator, you have an image and you are convolving with this kind of stuff. Now we understand, okay, we have seen it only in one direction, but this is kind of average. Okay, so in this direction we are computing an average. In this direction we are computing a derivative. And then, so we are computing derivative in y, derivative in x, then we are computing, so actually they are called g because they are approximations of the gradient. Then the gradient is a vector, okay? So let's remind what the gradient is. So let's go. So the gradient, so let's say that I have an image. You have an image. So an image is a scalar function. So that means that you have x, y, and then you have y or xy. So it is a surface. It's a surface that for every x and y gives you what is the height or the intensity of that image at that point. But then you can compute the derivative, split gradients, right? So you can compute the gradient. The gradient is the direction in which the function decreases most quickly. So it is decreasing most quickly in that direction. How do I compute the gradient? So the gradient of an image is a vector. It is partial derivative of y with xy with respect to x, and then the partial derivative of xy with respect to y. But these partial derivatives, we know what they are. So it is the derivative along x, the derivative along y. And we know that I can compute derivatives, or I can approximate derivatives with this kind of convolutions. So, and if it is a vector, it will have, so it is a vector, so it will have an x component and a y component. And then I can compute what is the module of that vector. So I can compute what is the module. I'm sorry. I can compute what is the module of the derivative of y. I will drop the location. So this will be the derivative of x plus the derivative of y squared. So that is what Revit is doing. So Revit is doing that. Revit has defined a way of approximating the derivative. So it has the shape of the derivative, but then in this direction it is an average. So it is computing the derivative in one point, the point on the left, the point on the right, and computing the average of the three. So to be a pure average would need this 1/3. But scalars, again, scalars are not important. Then we compute the gradient of that. So the module of that gradient, we can compute the direction of that. And then we can see examples of how the gradient looks like. Okay, and this is what we have done here. So we have done that. And then we have put a threshold. So if the gradient is larger than something, then I say I have a border. We don't have the results anymore. So we can compute the gradient, and if the gradient is something is larger than a threshold, then we put it to 1, or we put it to 0. Questions about this? Okay, so then otherwise we move on to the next topic. That is frequency filters. And this is the first use that we will make of the Fourier transform. So we used, we explained the Fourier transform. We understood that most of the image content is in the faces. We also understood that an image is made of the sum of this kind of waves. And now we will use the Fourier space for something that is computing filters. So let's go back to what we know from one dimension. So in one dimension, let's put it this way. So we have x of t, then this is whatever it is. When we do the Fourier transform, now we are in the Fourier domain, and this is the axis omega. As we said, it was omega radians divided by second, and this is x of j omega module, because it is a complex number that then I cannot draw it, and we always make this kind of simplified representation. What is interesting here is that there is some maximum frequency. So our signal is limited in frequency. But this is for continuous signals. If we have a discrete signal now, I have the same, but now my axis is n, I have x of n, then I have some substance here. The same over here. Then I do the Fourier transform, and we call it the discrete Fourier transform. And then what we have here is x of j omega. This is omega. And we know that this is periodic with period 2 pi. It also goes to the other side. And we know that the sampling, so the sampling is this difference between these two. So we know that the sampling has to be, let's call it, period of sampling. So we know that the period of sampling, so the frequency associated to this, must be larger than twice the maximum frequency, this one here. Because otherwise, so how is this condition called? Nyquist condition. Okay, so this is called the Nyquist condition. And if we violate the Nyquist condition, what happens? We have any risk. Yeah. So we cannot recover, if you violate this, you cannot recover from the samples, you cannot recover the continuous signal. Okay, so yeah, this is 1D. Now, in one dimension, I may be interested in isolating different frequency bands. I can say, I'm very interested in this area of my signal. So I can put a low pass filter. I have to identify that area. And I may be interested in a different region. So let's say I am interested in the high pass, in the high pass filter. So this is a high pass filter. The same here. Something like this. Okay, so we may design high-pass filters, we may design low-pass filters, and we can do the same in Fourier space with images. So with images, we have an image. So we have this image. When I do the discrete Fourier transform, I know it is periodic. Okay, so these points are minus pi, pi. This point, this is 0. This is the 0, 0. These points are minus pi, pi, but now in the other direction. And I know it is periodic. So this is equivalent of these triangles. So we can make sigma. Okay, so this is my sigma. So this is the equivalent of this triangle here in one dimension. And I know it is periodic. So being periodic means that I have extra copies now up to 5. So in this direction, I have an extra copy. But in this other direction, I also have a copy. So, and in this other direction, I also have a copy. So this extends infinity in all directions. Now, I can do low-pass filters. My low-pass filters were a low-pass filter here, and I would be selecting all these regions in Fourier space. And I can also do, so let's make the low-pass filter, let's fill it. Okay, this is my low-pass filter. My high-pass filter was green, so my high-pass filter, I was selecting a frequency, and then I was choosing all these areas. And I'm doing the same in all other copies. So in all other copies, I'm doing the same. This copy 2, and so on. So all these areas, I have 1, and here I have 0. It's the same that we are having here. So I'm having here a 1. Then outside that area, I'm having 0 in my field. And we know how to. So these are filters. They are filters, and these are linear filters. So let's go back to what we know in one dimension. So in one dimension, if I do this low-pass filter, because that's I construct a signal that is a low-pass filter. So I say my signal is a low-pass filter of my input. Okay, so it must be x of n convolved with the impulse response that is a low-pass filter. And because I can design my filters in Fourier space, I can do the Fourier transform of this equation. this equation, and then I get something like this. So my equation now we transform into this one. The Fourier transform of this is the Fourier transform of this times the frequency response of your field. So what we are drawing here, is this response. This is called the transfer function. And this one is called the kernel, or it is also called the impulse response. Why it is called impulse response? Because if I use an impulse, my x of n is an impulse, my output is just this one. Okay, so yeah, so that means that I can design my filters either in Fourier space or I can design it in the real space. I have the possibility of doing both. And actually for low pass filters this is very simple. So for a low pass filter, it looks like this. This let's say C. Then repeats. Then this is very simple. This is what is the inverse Fourier transform of this. So we now go to real space. This is a step function. This is a what? Sink. Okay. There are small details. It is a sink for. It is a sink. I don't know where we are. It is a sink for continuous signals. Here it is a sink. In these signals, it's not a sink, but it is something very similar to a sink. So it is something like this. So sine of you would have to look specifically on the formulas. Okay, but it is something divided by 2, divided by sine, and divided by. Look at it specifically the formula, but it is something very similar. Okay, so it looks almost like a sink. Okay, so a sink, pure sink, would be, and writing here in red. So this is not okay, but it would be something like this. So, and divided by omega c. So this is a sink. And this is almost a sink. Okay. So it is the ratio of two sides. Okay. So yeah, but in any case, this one looks like time shift. So it is a response that is in time shift. And then it is periodic. Remind that y, and then at some point it is made periodic. So let's say that this is our unit. This is our unit copy, and then it is periodized. Okay, because the discrete Fourier transform is periodized. So we are here. So when we make this discrete Fourier transform, this one is periodized. Okay, the FFT is doing that. Okay, very good. Then I can design my filters either in Fourier space or I can design them in real space. The problem with real space is that it is not so convenient, so it is not so easy to define these shapes. it's much easier to do it in Fourier space. So that is one of the reasons why we use the Fourier transform. The other reason is that when you have to implement it, you can implement both. So you can implement this one. So you can implement this one in real space. So you can construct a program that does that. And you can also construct a program that does this, but now in Fourier space. And the thing is that this one is much faster than this, all this. Okay. So doing filters in Fourier space, it is very fast. So that is also why we do filters in Fourier space. So we have two reasons. First, implementation is faster. And second, it is very easy to design filters in Fourier space. Okay, so let's do it now with images. So this is the property that I have used here. So when you have a convolution in real space, you have a multiplication in Fourier space. So this is the property. And here we have a graphical representation of that. So let's say that I have this image. This is the Fourier transform, or the amplitude of the Fourier transform. I want to convolve it with this mask, and then I do the Fourier transform of the mask. I multiply the two point by point. This is what this formula is telling you. So this formula is telling you have to multiply for every omega. You have to multiply these two functions. You have to do the Fourier transform of this, do the Fourier transform of that, multiply point by point, you get this one, and then you do the inverse Fourier transform. What we are doing. So the two Fourier transforms, we multiply, and then we do the inverse Fourier transform. So this one, this image, is a convolution of these two. And just a little bit of code to do that, but you don't have to pay attention to these things. This is the same story as we discussed yesterday about the origin, these things. And now we start to design our filters. Okay, so let's say that I want to define a low-pass filter. So a low-pass filter, that one there. So let's say that I design a filter. I design a filter. So we are in Fourier space. So Fourier space goes where I think. So I design a filter. This is omega. This is my filter. That is 1 over omega. Both sides. 1 over omega. So this is a low pass filter. And we are in 2 dimensions. So now we will have, so instead of actually, we can even in 1 dimension. If I put 1 over omega, this side has negative omega, so negative frequency, so it would be inverted. So I don't want that. So my filter is this one in absolute value. When you have 2 dimensions, now you have 2 axes. You have omega y, omega x. Now here you have the filter. And the frequency is now a vector. So your filter could be 1 over the module of that vector. And then it will be a filter like this. So that for every current point here, you have what is the amplitude, and the amplitude is that expression. And this would be a low-pass filter. This is what you have in here. This is 1 over the module of the frequency. And you can do the opposite. So what if I design my filter? What if I design my filter such that my filter is this one. So now my filter will look like something like this. So it's a kind of cone. So this is the module of the filter. This is omega y, this is omega x. It looks like this. And the zero frequency is multiplied by 0. So that means it is a high pass filter. So the higher frequencies are multiplied by larger numbers than the small frequencies. So low frequencies are dampened and high frequencies are boosted. Okay, so yeah, also something very interesting. Do you remember? For continuous signals. Continuous signals, I can compute this derivative. I can define a transformation that takes an input and computes the derivative of that input. Now we go to Fourier space. So we go to Fourier space. So I have done the Fourier transform. What is the Fourier transform of x prime? It's j omega Fourier transform of x. Do you agree? So this is my filter. So if I want to compute the filter, if I want to design a filter that computes the derivative, this is the filter I have to design. And if you look at this and this, it's almost the same. You see? What is the module? What is the module of this filter? So the module of this is the module of j omega, the module of that, and this is the module of j times the module of omega, and the module of j is 1, so this module of omega is what we have in here. So these kind of filters that have this response, this omega, this is module of j omega. So this kind of filters with this response, we are kind of estimators of the derivative. And now we have made the connection to edges. So we started the previous lecture, we started presenting edges as approximators of our derivatives. So we're here. So we presented all these kernels as a way to approximate derivatives. And now we have the same kind of stuff, but now in Fourier space. So we can compute derivatives with this kind of filters here. But now in Fourier space. They are not exactly the same. So one is not exactly the equivalent of the other, but they aim to compute kind of similar things. Okay, and then we can put a scalar in front of scalars. We don't care about the scalars. So let's say that I want to design an ideal low-pass filter. So an ideal low-pass filter would look like a step function. So this is the Fourier space. So it is 0 all the time. Then at very low frequency it is 1, and then it is 0 again. And then I can compute what is the impulse response of that. it should be kind of sync. So here we have, this is a one-dimensional representation. So here we have both at the same time. So frequency and the oscillatory part is the spatial response. So we have a kind of sync. And now we can compute, we can do Fourier filters with that. So also, if I make this band smaller, so a narrower low-pass filter, then my impulse response will be larger. And this is again this uncertainty principle. If something is very compactly supported in one of the spaces, the other space has to be wide. Okay, so if it is very narrow in Fourier space, it has to be very wide in real space. How do we compute filters with this? So we take an image, we do the Fourier transform, we multiply by the ideal low-pass filter, so this is the multiplication of the two, and then we do the inverse Fourier transform. That is what we get. So now we can blur our images, and as we said yesterday, blurring is not always bad. If you have a lot of noise, blurring is good because it is averaging around. And yeah, this is just for comparison. So you can see. Okay, high-pass filters. So high-pass filters is the opposite. So it is should be one everywhere except for a region. And then this is the impulse response. And there is a very simple way of knowing what the impulse response of something, a low-pass, a high-pass filter should be. Okay, so let's say that we have here, this is omega, this is low-pass filter as a function of omega, and it is this, and then we have said, I will be loose here, okay? But we know that this is n, this is kind of c. I put it in quotes because we know it is sine divided by sine. Okay, so now, let's say I have a high-pass filter. So if I have a high-pass filter, it would be something like this. So I'm only representing the part between minus pi and pi. I'm not making it variable. But in this region, minus pi and pi, it looks like this. Okay. But I can say, okay, this one, let's make it different. This one is 1 minus the low-pass filter. And this is my low-pass filter. And this is what I have. So it would be 1 minus this piece. And now, what is the inverse Fourier transform? I will do the inverse Fourier transform. Minus 1. Then it will be the inverse Fourier transform of 1. But what is the inverse Fourier transform of 1? So the high-pass filter of n will be, what is the inverse Fourier transform of 1? Delta. So it will be delta minus a single. Also, what is the sum of all these values? Can I know? So I take, this will have some shape. Can I sum all those values? I can sum them. And what is the result? zero. Has to be zero. Why? Because this sum is an impulse, a frequency response. Is the frequency response at zero. And at zero frequency, I have zero. This high-pass filter at zero frequency has zero. So all this sum has to be zero. Doesn't happen with low-pass frequency, does it? So all this sum has to be 1. So samples here. All these samples, the sum of all these samples has to be 1. The sum 1, you see, you have the delta minus the sigma. You have the delta minus the sigma. And the sum of all these values has to be 0. Let's make a break. If I don't note the time, just let me know. Esta imagen es la suma de todos estos valores tiene que ser cero. Y aquí lo vemos en un corte. ¿De qué?
No termino de verlo.
¿Que por qué es
Sí,
cero?
por teoría, sí, justo. O-
Claro, por teoría. Que... A ver, ¿cuál es la transforma de este? Lo voy a hacer con uno, ¿vale? Que es más fácil. A ver, la transformada de un billete de mi vector para impulso. Esto es la suma para, no sé, en el periodo que estamos en transformada completa de la HDN por que elevado a omega n. Pero vamos, pues yo voy a coger omega 0. A ver quién es h elevado a omega 0. A ver quién es ese. Pues ese es la suma de la HDN por elevado a menos j 0 por n. Pero 0 por n es 0. Y la exponencial de 0 es 1. Luego esto es la suma de los HDN. Tenemos HDN por n. O sea, lo que ocurre en 0 es la suma de toda la respuesta de impulso.
Claro, pues antes mismo que se multiplica no suma de... Vale, ahora sí. Muchas gracias. sea, ¿dónde están las puestas? Yo me he quedado fría ahora, ¿cómo salió? Está acá.
Sí, es tu proyecto.
Cuando has estado explicando esto, has dicho que primero de aquí a aquí como que había otra habilidad que es diferentes.
Y ahora esta la aceptamos de los mínimos, ya se ha aplicado el secreto. Nada. Bueno, venga, vamos a seguir. Venga, Veronique Sánchez. O sea, ¿cómo se ha hecho? ¿O cómo? ¿O por qué es bueno para el ruido? ¿Por qué es bueno para el ruido? Vale. Vale, pero no. O sea, la pregunta es ¿por qué emborronar es bueno cuando tienes ruido? Cuando tú tienes ruido, vamos a pensar en Fourier qué es lo que está pasando. Yo tengo, de hecho, este es el tercer uso que le vamos a dar a la transforma de Fourier. Voy a poner el modelo sin las funciones, sin un filtro, pero luego lo extenderemos aquí. Vale, yo tengo una imagen. Vamos a ponerlo una imagen. Tengo una imagen que ha seguido. Y esta imagen es una imagen ideal más un ruido. Que en cada posición tiene un valor diferente. ¿Vale? Si yo ahora pienso esto en Fourier, si yo esto lo que hago la transforma de Fourier, llamada de Fourier, que utilizar sí. O sea, siempre que no haya problemas con la notación, que se entienda que lo que estás haciendo, da igual que pongas E o la J o omega, pongas omega solo. O sea, si lo que quieres indicar es que depende de lo que. Claro, ¿esto qué es? Pues voy a hacerlo en uno de estos, que lo puedo pintar más. Yo tengo mi eje omega, voy a hacer uno de estos. Y aquí lo voy a representar todo, la I, la J y la E. Vale. Este es mi espectro. De hecho, lo que estoy representando es el módulo de cada uno al cuadrado. A esto como lo habíamos llamado, el módulo de cada uno al cuadrado. La densidad espectral de potencia. La PSN. Vale, pues esta es la I. Esta de aquí es la I. Ahora lo que pasa es que encima de esto tengo ruido. Vamos a suponer que tengo ruido blanco. Entonces, si yo hago un filtro paso bajo, aquí, y me quedo justo con la frecuencia donde tengo más señal que ruido, todas estas frecuencias me las estoy quitando. Pero es que estas frecuencias en el fondo eran peor, porque era peor tenerlas, porque tenía más ruido que señal. Pues si tengo más ruido que señal, mejor te quitas esa frecuencia, ¿no? Luego, hacer filtros paso bajo cuando tienes ruido está bien, porque cuando tienes ruido, vale que a baja frecuencia predomina la señal, pero a altas frecuencias predomina el ruido. No sé.
Pero, claro, el ruido de la imagen como tal, ¿cómo se...? O sea...
Eso lo vamos a ver más adelante. Vamos a ver, pero vamos, si quieres ver alguna fotilla, por ejemplo. Pues así. Aquí se ve muy bien, por ejemplo. Esta es la imagen sin ruido y la imagen con ruido.
¿Y eso se distingue de función de imagen o no? O sea,
Si yo emborrono, lo voy a ver mejor que esto. De hecho, a ver, por ejemplo, noisy image y de noisy. Mira esta. Aquí he tenido que emborronar, seguro. Ya, de hecho, with impulse, causa. O sea, de aquí a aquí estoy emborronando seguro, pero lo veo mejor aquí que aquí. Hay otro ejemplo por ahí que haya. Aquí sale lo mismo, pero con detección de voces, que ya sabemos cómo se hace. Muy bien. Más preguntas. Okay, so then we continue with the theory. Okay, so now we had high-pass filters, so we reasoned that the sum of all these values have to be 0, and then we can follow the same process, but now in the Fourier space. So you take the original image, compute the power spectrum, so compute the Fourier transform, then you design your filter in the Fourier space. You multiply, so if I multiply these two, point by point, this is what I get. Okay? So I get whatever I had where the filter was 1, and then 0 where the filter is different from 0. It's different from 1. And then you do the inverse Fourier transform, and this is what you get. So we have the borders, because we know that high-pass filters, okay, they are not kind of we have said before that these kind of filters, they are computing borders. They are computing, this is omega, this is the module of the filter. And we said that these kind of filters are edge detectors, but this one, that is a high pass filter, is a kind of very, very crude approximation to that. Okay, so when it is smaller than this value, we put to 0, and it is larger than that value, we put to 1 rather than omega. So it is a very crude approximation, but we should see the borders of our image. And then we can compute ideal bandpass filters. And ideal bandpass filters, now we know the trick. We can subtract filters, so we can design a low-pass filter with a radius, another low-pass filter with a different radius, and then we compute the difference. So this is the same as we did with the high-pass filter, 1 minus our low-pass filter. So instead of now 1, we have the difference between 2 low-pass filters. So this is the filter with a radius 1. This is a filter with radius 2. Which one of the two? So these radii are frequencies. Okay, so which of these two frequencies is smaller? Rho 1 or rho 2? 2. Why?
Because of the
Because this image is smoother, so it is much more blurred. So that means that in Fourier space it has to be narrower. Okay. And then we can compute the difference, this one minus this, we get that one. So it is a bandpass filter now. And this is the spectrum of the filter, and this is the multiplication of the two. So, yeah, we said something about the uncertainty relation. That is, if something is wide in one of the spaces, it has to be compact in the other. And that means that if you have something that is very, very compact in one of the spaces, it has to be wide in the other. So wide means that if I have a step function, I have a sink, and the sink goes to 0, but at infinity. So it goes to 0 relatively slowly. And because of this, I'm convolving with this signal that is going up and down. So that means that if I take a step, so for instance, I do an ideal low-pass filter of this image, this is what I get. And then I see some ripples that are really annoying. And these ripples come from the convolution with this sink. Okay? Because the sink goes to 0 relatively slowly. All those rings there. Okay, so let's see if I can design a filter that is more or less compact in one domain, so in the frequency domain, and more or less compact in the spatial domain. And that filter is the Gaussian. So the Gaussian is compact in both, or relatively compact in both. You know that the Gaussian has this. So let's so the Gaussian, the interesting part of the Gaussian is this one, this exponential of minus, let's say x. I will center it at 0, divided by 2 sigma squared. This is a square. Okay, so if I ask you f of x is equal to 0, what is x? What is the x that makes the Gaussian to go to 0? Infinity. So it only goes to 0 at infinity. So that means that this function never vanishes. So this is f of x. Okay? On the other side, it is the same. So it never vanishes. But in practice, okay, so if I go further than, I don't know, If I go to 6, I don't know the exact value, you have to compute, okay? But let's say that this at 6, this f of x is in the order of 10 to the minus 10. And here it is 1. I don't care, it is not 0, but I don't care. It is so small that I don't care about it. So strictly, it never goes to 0. In practice, it does. Okay, so it is so small that I don't care anymore. So Gaussians are not strictly compact in any of the two spaces, but in practice, they're almost compact. Okay, so they go to 0, or almost 0 eventually. So, yeah, it has another advantage. The inverse Fourier transform of a Gaussian is another Gaussian, and the same in the other direction. So the Fourier transform of a Gaussian is another Gaussian. If it is wide in one space, it will be narrow in the other. Okay, so then I don't have ringing anymore. So this is the equation of the Gaussian. How does a two-dimensional Gaussian looks like? It is the product of two Gaussians. So the two-dimensional Gaussian, well, it has. Okay, so this is the formula for the one-dimensional Gaussian. And what is the formula? Let us write the full formula for the one-dimensional Gaussian. Okay. So I'll write it G. So G of x, so that is my Gaussian. Is square pi sigma squared exponential of minus half of x minus mu by sigma squared. And I can write this in this way. So I can write this as 1 sigma, and then exponential of minus half, and then I would write x minus mu, 1 divided by sigma squared, and then x minus mu. It's the same. Okay, now let us extend it to two dimensions. So now instead of x, I will have x and y. Okay, so now we have g, and this g depends on a vector that has x and y. So you know the covariance matrix, right? So what is this sigma? This sigma is the variance. This is the variance. You may remember the definition of variance. So it was the expected value of your variable minus the mean of that variable squared. Do you remember that? The same way, you could define the covariance matrix. So if you have two variables, now I will draw the xy subindexes. So I can define a matrix. So this matrix will have the variance of x, the variance of y, and then the covariance of x and y. Do you remember that? This is defined in this way. This is defined this way. Now with y instead of x. What about this one? So this one was the expected value of x minus the mean of x, y minus the mean of y. Okay, so now we have the covariance matrix. So this is the equivalent, kind of equivalent. Now, in one dimension, you have a variance. In two dimensions, you have a covariance matrix that somehow encodes the covariance, the variance and the covariance of everyone. So let us extend this expression now to two dimensions. Okay, so I will have this one, and again, this you have to believe me. this is instead of sigma, we will put the determinant of that matrix. But the determinant seems like this kind of good summary. So what is sigma squared? It is a summary of how the data is varying. So the determinant of sigma of the matrix, of the covariance matrix, it also seems to be a good summary. Okay, now we continue. So minus a half. Okay, x minus mu. But now I have two variables, so I will have two means. So I will have the two variables minus the two means. So now the mean is also a vector. Now I have the inverse of the variance. But the inverse of the variance, I can put the inverse of my matrix. And then I can put the same. So it is a relatively straightforward transformation. There is a drawback here. Okay, so let's make, let's count, or let's look at the sizes. These are vectors, okay? So this is 2 times 1, this is 2 times 2, and this is 2 times 1. So can I compute that? I cannot. Okay? This matrix multiplication is not correct. So I need a transpose there. I need a transpose, and then this is 1 times 2. So this is correct. Okay, but now we have extended our Gaussian from 1 dimension to 2 dimensions. There is a trick. Let's say that this value is 0. If that value is 0, then you can show that this one is equal to a Gaussian in x times a Gaussian in y. And that is what you have in the slide. Okay, so in the slide, what you have is the multiplication of these two Gaussians. So this is Gaussian. But that only happens if x and y are independent. And they look like this. So it is a kind of bell, but now in 2 dimensions. Okay, good. Then I do my filter with the Gaussian filter, and I don't have the ripples anymore because I'm convolving with something that doesn't have ripples in the real space. If it doesn't have ripples, that means that I will not get ripples when I get to edges. And can compare to the ideal low-pass filter, and yeah, we can look at again the same process as we did before. So this is the Gaussian in Fourier space. This is the corresponding Gaussian in real space. We are representing both there. Yeah.
But the Gaussian filter is a type of data low-pass filter.
Yeah, because if you put what is my frequency response? So my frequency response is, let's say that my filter is Gaussian. Okay, so a low-pass filter of omega that is a Gaussian of omega, okay, the sigma. So like this. So, and this is omega. So that means that the low-pass, that the low frequencies can go through, but the very high frequencies they cannot go through because they are multiplied by something that is close to 0.
So if we blur the image.
They will blur the image, yeah. Yeah. So, and if you make the Gaussian larger in one domain, it will be narrower in the other. So this one will blur less. So here we have some examples. So we take the original image, the power spectrum of that image, the low-pass filter in the Fourier space, we multiply the two, and then we blur. And we can design high-pass filters. So high-pass filter is 1 minus the Gaussian. So 1 minus the Gaussian is a high-pass filter. So, and we know what is the impulse response. It is delta minus the Gaussian. So that is the impulse response. And then, again, we take the original image, multiply by dark filter, and then we get the edges. We can make the Gaussian larger, so we will skip more frequencies. So you can compare that one, this one. So in this one, we are losing very few. Okay, now this is the multiplication of it. Okay, so yeah.
If it has a low pass filter, well, we want to have the Gaussian filter and the low pass.
Ripples. So if you do a low pass filter as it is, you get ripples because you are convolving with something that is oscillating. But in the Gaussian, you don't have these ripples.
And it's better.
It is more pleasant. So if I take that image, convolve with something, and this is the result, do you like the result? Or you think it is artificial compared to the original image? It is artificial because all this rippling didn't exist. All these bars, they didn't exist. But now with the Gaussian low pass filter, it is not here, but you don't get those ripples because you are convolving with something that doesn't have ripples. Yeah, we could see it with the trains. Yeah, here we have it with the Gaussian. So you don't get the ripples anymore. I was looking for this image. High pass filters, band pass filters. Yeah.
And when we have to use one or another, if it's the same for you.
But it is not the same. In the ideal low pass filter, you get ripples. In the ideal filters in general. So if you do a high pass filter, you also get ripples.
But the result is the same.
The result is not. So it is kind of similar. It is like you are multiplying by this function or by this function. So they are not too different, but they are not exactly the same. So they try to get kind of similar effects. So just to keep the low frequencies. But this one multiplies by 1 here and 0 there. And the other one, this one here, this one, it is multiplied by 1 here, but then 0.9, 0.8, and then it goes smoothly to 0. So the one that drops abruptly, it creates this rippling. The other one doesn't create it.
Yes, I know, but the thing that I don't understand, when we have to use one or another.
Depends on what is your purpose. So if it is to produce an image that that is visually pleasant, I would use this one. I would use this one because I don't have the ripples anymore. If I have to, we haven't seen this yet, but if I have to preserve the information content as reliably as possible, then I have to use this one, even if it is not visually pleasant. Okay. Then we can create bandpass filters by subtracting two Gaussians. And it is the same trick as we did with the ideal pass filters. And here we have an example. So this is with one sigma, another sigma, and we subtract the two, we get this one. And yeah, this this is the representation of the bandpass filter in Fourier space, the impulse response. This is a profile of the impulse response. And what is the sum of all these values? Close to zero, because the zero frequency is removed. Very close to zero. It doesn't need to be exactly zero, because the Gaussian never vanishes. But it has to be close to zero. No, actually it has to be zero, because it is Gaussian minus Gaussian, both are at the origin are 1. So 1 minus 1 is 0. Okay, so yeah, more representations of the same idea. So original image, the power spectrum of the original, then the filter, Fourier space, we multiply the two, and then we do the inverse Fourier transform. We get this one. We can compare the two. Yeah, I was looking for this comparison between low-pass filters and Gaussian. So here we have the ideal low-pass filter, the ideal high-pass filter. Here we have the Gaussian versions. So you see the ripples here. You see the ripples in the trains. So the Gaussian is somehow nice. And bandpass filters, and again we see the ripples. And the Gaussian bandpass filter, we don't see them. And what about the power spectrum? So we have the original image, the power spectrum, that is the that's the node on the power spectrum. So the power spectrum, we have said this at the beginning in some of the previous classes, but power spectrum of an image is the Fourier transform. This is by definition. This is the Fourier transform of the autocorrelation of that image. And the autocorrelation of that image, depends on a lag. So that is a vector. So what is the autocorrelation of an image? So it is the expected value of that image times that image plus the lag. So that is the definition of the autocorrelation. And in case that I is deterministic, it is always the same image, always the same image. Okay? That doesn't happen if you have noise. If you have noise, it is not always the same image. Every time you have a different realization of noise. But if I's image is deterministic, then this is the Fourier transform of the image. This is a vector square. Okay? So in general, this depends on frequency. So in general, we always talk about this, but the full definition is this one. Okay? And this is true, but only for the deterministic images. So if you forget about the noise, that is true. Okay, so we take the original image. This is the power spectrum. That's the model of the Fourier transform square. This is the phase. Then this is the power spectrum if you multiply with kind of Gaussian. So take the original power spectrum, multiply by Gaussian. This is what is left. This is the original image or the blurred image, and this is the phase. And why doesn't the phase vanish? So it doesn't go to zero. This one seems to go to zero. This one doesn't seem to go to 0.5. Because the Gaussian never vanishes. So let's say that let's look at this. Okay, so I'm filtering my image. So I have my image, Fourier space, that is my original times my Gaussian. Okay, this is my Gaussian. the Gaussian never goes to 0. Okay? Now, let us write this in this way. So it is the modulo of I times the phase of I, that frequency, times modulo of G. But modulo of G is a Gaussian. So a Gaussian is a real number. So a Gaussian is a real number. So it will have that part. What is the phase? Phase is always 0, always. The phase of a real number is, of a positive real number, is 0. Okay, so now this, we continue here. So this will be, what is the amplitude? So the amplitude is the amplitude of the region times the Gaussian. This is the amplitude. And the phase will be the phase of the region at that frequency, plus 0. I don't have to add plus 0. So now, right? So this is amplitude, this is phase. So the amplitude changes, but the phase does not. The phase doesn't change. Sure. Yeah, this is original. Yeah, also, we have seen that we can compute high-pass filter images. So now, the high-pass filter, we have seen it here. Okay, so this is, for instance, high-pass filter. So this one is detecting edges. Why restricting to low pass, high pass, this kind of stuff? Why can I not design this filter? So I can define a filter that is 1, so everything goes through, plus a high pass filter. So my response would be something like this. So it will start at 1, then it will go up. This is go up. This is omega. This is h of omega. So now I can boost high frequencies. As you remember from the first lectures, that as humans, we are animals that like we can only see edges. We only see edges and interpolate the data, the space in between. So having edges is good for us. So why can I not take this image, and add this one? I can do that. That is called a sharpened image. So we can now reinforce the edges. We will see this image sharper than the original. So convolution can be used for anything. So it is not only for blurring. So it depends on with what you convolve. If you convolve with something that boosts edges, then you will see better your image. If you convolve with a low pass filter, then you will blur it. And blurring is not necessarily bad. We saw it with the denoising. Actually, if we look at the denoising, why we don't like this image there? The one with a lot of noise. What is the one with a lot of noise? Because it has a lot of edges. So the derivative has a lot of, you are in a pixel and then the next pixel has a totally different value, the next one has a totally different value. It has a lot of edges, so we don't like that. We like better smooth images. Even this one, if it is too smooth, but it still preserves most of the information there because the important edges are preserved. So all these edges there, they are preserved. So we can reinterpolate what is in between. So the noising and blurring, as long as you preserve the edges, that's fine. Okay, so let's look at another one. So this has a lot of edges. And the derivative is high everywhere, while this one, the derivative is low in most places, except at the edges. Any question to this, for this? No. Then let's go for the exam. So the exam is here, this one today. The exam you have to do it in class. Those outside class cannot do it.